Okay, so this video accompanies the notes for section 9.7, and so we're dealing with matrices here, which is the plural of matrix. Matrix is just a sort of an array, a way of storing information. So instead of a variable having just one value, we can have a multitude of values kind of stored in this, say, this variable A, except it's not a variable, it's a matrix. And so a matrix has a set number of rows and a set number of columns. And so here we can see A, capital A. We use capital letters to denote matrices. Matrix A is a row, 3 rows by 4 columns. So we call this a 3 by 4 matrix. All right, so we always give the row number first and then the column number. So we say it's a 3 by 4, meaning that it has 3 rows, 4 columns, or a total of 12 elements, 12 different values. All right, so we use the little subscripts behind the letters. So small a is going to mean the element of matrix A. And so it's A with a subscript 1, 2. That's not A subscript 12. It's A subscript 1, 2, meaning row 1, element 2. And so that would be the value of 7. All right, see how that works? So number 2, A sub 2, 1. That would be an element in the second row, first column, so that's negative 5. All right, so A sub 2, 3, that's going to be the second row, third column, so that should be 3. All right, A3, 2 is clearly different than A2, 3. Well, it could be the same, but in this case, it's different. It's the third row, second column, so that should be 10. All right, what is A3, 2? That should be the last thing there, 7. And then A sub 3, 1, that should be just a 4. Okay, so we can denote which element of the matrix we're referring to. All right, so let's do an example here. You decide to start selling t-shirts with some cool silk screening designs. There are 3 sizes of t-shirt, small, medium, large, and there are 4 colors. You can either get a green t-shirt, a black t-shirt, a white t-shirt, or a yellow t-shirt. All right, you could store how many t-shirts you have, right? Store the number of each type of t-shirt in your warehouse in a matrix. So the first row represents all your small t-shirts in the 4 different colors. The middle row is the number of medium t-shirts in the 3 different colors, and the last row would be the number of large t-shirts in all 3 colors, in all 4 colors. So clearly there are no medium blues left, right? Because there's a 0 in the second row, second column, which is medium and blue. Sorry, B is black. Okay. All right, so how many t-shirts are in the warehouse? All right, so how many small black are in the warehouse? Clearly 7, right? That's the first row, second column. How many medium yellow? Clearly 1, right? That's the second row, 4th column. Large white. All right, that's going to be 8. And medium green. All right, that's 5. All right, so you can store a bunch of information then in a matrix rather than just saying like the variable A equals 1 value and store that in a computer program. You could store a multitude of values in your program. I used to use these when I was doing computer programming. I'm sure it's more sophisticated now, but 20 years ago, 30 years ago, we would use matrices to store information. All right, if matrix B stores the number of shirts sold last month, and remember A was the number in the warehouse currently, then B plus A would equal the number of t-shirts in the warehouse at the beginning of last month. So find B plus A. So it's pretty intuitive. In order to be able to add these matrices, they have to be of the same size, right? So they have to both be the same number of rows and the same number of columns. These are both 3x4s, so we can add them up. All we do is we add up corresponding elements. So go ahead and do that. Pause the video if you want and add those up. All right, so I simply added the first element of the first row to the first element of the first row, first column in both matrices. So 7, the next one was 1 plus 7 is 8, 0 plus 3 was 3, and so on, right? So we simply add up all of the corresponding elements of the two matrices that are the same size. Again, if they're not the same size, if they're not both 3x4s, we could not have added them. If one was a 4x3 and one was a 3x4, cannot add those. All right, so in the next examples here, 4, 5, and 6, we're giving you 3 different matrices, matrix C, D, and E, and want you to perform the following additions. Pause the video and try all those. Okay, so you can see that C and D are not the same size. So adding C plus D, that's just not possible. All right, so C is a 2x3, D is a 2x2. We cannot add matrices that are not the same size. All right, so C and E, hopefully you added those. You just add up the corresponding elements. And then E minus C, just be careful. You want to make sure, especially when we're adding and subtracting negative numbers, it's easy to lose a negative. So we're subtracting E minus C. All right, and so we should get this as a result. Sometimes it's nice just to take the C and change all the signs to negative, opposite signs, and then you can add them. So if that helps, you can do that as well. Like, if we were doing subtracting a binomial or a trinomial, we would often take this negative and distribute it to all of the elements or all the terms in the second polynomial. But here we might just swap all the signs, sort of distribute, if you will, the negative to each of those 6 elements. All right, let's look at example 7. So you decide that last month's sales, going back to the t-shirt example, you decided that last month's sales were typical. Do you want, so you want to figure out how many you will sell, how many t-shirts you're going to sell over the next 3 months. So however many I sold last month, I'm going to use that as a prediction how much I'm going to sell over the next 3 months. So how many t-shirts of which type would I end up selling? So we're looking for 3 times B. So we take 3 times B, we have a 3 out in front of the matrix, and we simply distribute that 3 to each of the terms. Each of the terms in the matrix simply gets tripled. We call this type of multiplication a scalar multiplication because we are just simply taking everything and multiplying it by a number 3. Okay? So that's a simple kind of multiplication. The next type of multiplication is going to get a little bit more complicated. All right, so if we have 2 matrices that are equivalent, so 2 matrices are equal when each pair of corresponding elements of the matrices are also equal. So use that idea to solve. See, for example, we have 5 is equal to 5, and 6 is equal to 6, and 7 is equal to 7. That means x squared must equal 25, and y must equal 9, and 2z must equal 12. So simply solve those and set those, create those three little equations and solve for those. All right, multiplying two matrices. Okay, so now this is a little bit more complicated. This is the more challenging type of multiplication. Scalar multiplication, that was easy. It's just a number out in front and you're multiplying each of the elements. Here, we're multiplying two matrices together. All right. So it's not always possible. Just like when you're adding, you can't add if they're not the right size. Same thing here. So let's assume that we have two matrices, A and B. A is a 2 by 3 matrix, and B is a 3 by 4 matrix. The multiplication is possible, and it will result in a 2 by 4 matrix. So matrix AB, if you will, the product of the two, will be a 2 by 4 matrix. So you can see that the number of columns in the first must equal the number of rows in the second. And when we go through the mechanics of multiplying these, you'll see why that has to be. And the result will be the row of the first by the number of columns of the second. So multiplying A by B gives us a 2 by 4. Multiplying B times A is not the same as multiplying A times B. Now, in normal multiplication, if I multiply two numbers together, if I multiply 2 times 3, that's the same as multiplying 3 by 2. That's something called the commutative property of multiplication. But there is no commutative property of multiplication for matrices. So A times B is certainly not the same as B times A, if it's even possible. It may not even be possible. And in this case, if I were to try to multiply B times A, you can see that the sizes would not be right? So then the first would have a row of 3 and a column of 4, and then this would have to be a 4 for it to work, and it would not. So multiplying, flipping them, A times B might be possible, and B times A would not necessarily be possible to do. And if it is, it will not be the same result necessarily, okay? All right, so let's look at A times B. So A, again, is a 2 by 3, and B is a 3 by 2. All right, so first of all, is this possible, multiplying these two together? So it's a 2 by 3, a 3 by 2. So yes, this is possible. Those two numbers have to be the same. And what we do to figure out what the result will be is we just use the row of the first times the column of the second. And that will be the result when we're done. All right, we haven't done it yet, but just knowing that you have to have the column for the first has to equal the row of the second matrix, okay? And then you sort of like figuring out what the result will be. It's the row of the first, and the column of the second that gives us our dimension. All right, so let's actually do this. All right, so we take the first row and the first column. In order to get this first element, let's call it E11, row 1, column 1. We take each element of the first row, one at a time, multiply it by each element of the first column, and we add them up. So we multiply 1 times 2 plus -4 times 3 plus 6 times 0. All right, so we multiply the first row by the first column, one pair at a time, each element at a time, and we add up those results. So we get 1 times 2 plus -4 times 3 plus 6 times 0. And of course, that's going to be -10. So E11 is -10. All right, to get the second, we take the first row times the second column. Elements, one at a time. What will those be? All right, so we get 1 times -1 plus -4 times 4 plus 6 times -2, or a total of 29. All right, so that 29 is the second element of the first row. All right, so pause this video and do the bottom row of our product matrix. All right, so you can see we multiply the second row by the first column this time, and then finally the second row times the second column to get the last one. All right, so hopefully you got that as your matrix, as your product of A times B. All right, so for examples 10, 11, and 12, I'm giving you 3 matrices, matrix C, D, and E. So go ahead and try to multiply matrix C and D together. Remember, you're going to take the first row, the 3 elements of the first row, times the 3 elements of the first column, which is really just only one column. Also, think about what matrix. What size matrix this is. So this is a 3 by 3, and this is a 3 rows by 1 column. And so, are they the right size to be able to multiply C times D? All right, and it is. And so what size will the result be? Again, we get rid of sort of these center 3's, and the result will be a 3 by 1 matrix. All right, so we're going to multiply the first row by the first column. Do those 3 products. Why don't you pause the video and try to multiply C times D. All right, so when we multiply, it's the 2 times -3, first row times the first column. So 2 times -3 plus -4 times 2 plus 3 times -2, times 4, sorry. So those 3 products get added up and they give us a -2. And then you do the middle row times this first column, and then finally the bottom row times the first column, and that will give us the 3 elements in our 3 by 1 matrix. All right, find DC. So you can see we cannot multiply C times D. C is a 3 by 1. D is a 3 by 1. C is a 3 by 3. So therefore, they don't have that middle value the same. So this one is not possible. Those 2 numbers would have to be the same, and they're not. All right, what about C times E? So we might add to this one. This one is a 2 by 3 here. Might add that just so we can see that. And so C times E, think you can see that those center values are not the same, so we could not multiply this one together. Could we multiply C times E times C? Yes, we could have done E times C, but C times E, that is not possible. Okay, so this is your homework for section 9.7. This is due next class.